Hello dear students, welcome to the next lecture on heat exchangers. In this lecture we will discuss some problems and the solutions from heat exchangers. Normally the types which are being asked for the university examination, ME302 heat and mass transfer of KT. Let's see the questions one by one. So going to the before discussing the questions, I want to rewind the topics which you have covered in the theory parts. In the first lecture, it was classification of heat exchangers. Yeah, in the first lecture, it was classification of heat exchangers. We had seen the different classes. Then we saw the concept of overall heat transfer coefficient, which we have already done in the very first module, conduction problems. Then the phenomenon called fouling and the additional heat thermal resistance due to fouling called the fouling factor, which is to be included while calculating the overall heat transfer coefficient of a heat exchanger. Next is the analysis of the heat exchanger using log mean temperature difference or LMTD. We know that LMTD can be calculated if we know all the four temperatures, that is hot water and hot fluid and cold fluid, inlet and outlet temperatures. If we know the four temperatures readily or temperatures which can be calculated from energy balance, then LMTD can be calculated, and this is in a way is used to calculate the heat exchange. Q is equal to overall heat transfer coefficient into area into LMTD. If we don't know this, then the analysis can be done by calculating the effectiveness using effectiveness NTU relationship. Remember, effectiveness NTU relationship is a relation which does not have temperature terms in it. And by knowing the effectiveness using any relation or any suitable chart for that, then the actual heat transfer can be calculated as a product of effectiveness into THI minus TCI. This method is used. But remember that in university there are 3 question papers have been is there in the as previous question papers of KTU, like the question paper for the examination held in May 2018, then the next year May 2019, and also one more question paper has come December 2019. I have shared you all the 3 question papers through ET-Lab, and I advise all of you to go through the question papers and try to answer the questions in the question papers from each topic. Anyhow, these were the things which we discussed, like we derived the LMTD for parallel flow and counterflow heat exchangers, as well as we derived the effectiveness NTU relationship for parallel flow and counterflow heat exchangers. All other type of heat exchangers, all these relations can be obtained from suitable charts or from equations which can be used. These were the things which we had discussed in the first 3 lectures, and I shared you the links of these lectures also. Now in this lecture we will discuss some problems, simple example problems only. How to calculate, the problems are meant for calculating the overall heat transfer coefficient and then find the heat transfer or the unknown parameter, etc. So we'll see the questions one by one. I'll go to the presentation mode here. We'll see the questions one by one. I'll read out the question. Determine the overall heat transfer coefficient U0 based on the outer surface of a steel pipe with an inner diameter of di is equal to 2.5 centimeter and an outer diameter TO is equal to 3.34 centimeter, and the material of the pipe having a conductivity K equal to 54 watt per meter degree Celsius for the following flow and fouling conditions. The heat transfer coefficient at the inner surface, that is for the two fluid, it is 1800 watt per meter square degree Celsius, and heat transfer coefficient at the outer surface is 1250 watt per meter square degree Celsius, and the fouling factor values for inner surface as well as the outer surface were given in the problem itself as 0.00018 meter square degree Celsius per watt. Remember, a fouling factor has a unit or dimension reciprocal to that of the heat transfer coefficient value. So fouling factor in a way stands for the resistance, additional resistance per meter square on the surface due to fouling. So in this problem, we can calculate the overall heat transfer coefficient. If we go back to our previous slide or the previous modules which you've already seen, fouling factor or the calculation of overall heat transfer coefficient calculation of overall heat transfer coefficient without fouling 1 by UA, which can be written in terms of 1 by UIAI, or which is also equal to 1 by U0A0, where UI is a overall heat transfer coefficient based on the inner area, UO is the overall heat transfer coefficient based on the outer area. So from this relation, 1 by UO is equal to AO multiplied by this relation, or UI will be AI multiplied by this relation. This is a case when the fouling factor is negligible or the surfaces are fresh surfaces, so that there is no fouling occurred on the surfaces. In case where there is fouling occurred for the surfaces, we need to incorporate the additional resistance due to fouling both on the inner surface as well as on the outer surface. So 1 by UIAI is equal to 1 by U0A0 is equal to 1 by HIAI plus RFI divided by AI plus log d out divided by di divided by 2 pi lk, like this. This is a relation for overall heat transfer coefficient. This relation is given in the data book also. You can get this value. So if you want to calculate overall heat transfer coefficient based on the inner surface, this relation is to be multiplied with AI. And if you want to calculate the same overall heat transfer coefficient based on the outer surface, this relation is to be multiplied with AO. So we can suitably do that. And one more thing to remember is that if there is no fouling and also the wall resistance, this term is negligible, then 1 by U is approximately equal to 1 by HI plus 1 by H out. Here we have also neglected the thickness of the wall. So this is an approximate relation. Any of these three relations can be used suitably. So now coming to the problem, to calculate the overall heat transfer coefficient, we can use the equation directly. U0 is equal to 1 by U is given by this relation. So U0 is equal to 1 by this relation. So overall heat transfer coefficient based on the outer surface as is required in the problem is equal to d0 by di 1 by hi plus d0 by di fi. Remember, this is a fouling resistance due to fouling. Resistance due to fouling for the inner surface. So this can be written the same way as we write for this. Plus now this is a resistance due to conduction through the wall. So d0 divided by 2k ln d0 by di plus f0, sorry, f out plus 1 by h out. Similarly, this is d out, not d0. So this is the equation for u0, sorry, u out. So substituting the values, we can calculate this for 87.1 watt per meter square degree Celsius. Now, one thing to remember here is that HI is 1800 and H out is 1250, and the overall heat transfer coefficient, this will incur a resistance 1 by HI AI, and this will incur a resistance 1 by H out A out. So the total heat transfer coefficient, the resistance will be more than resistance due to this and this. Similarly, the overall heat transfer coefficient value will be less than the lowest value among HI and H out. So here 487 we have inner or heat transfer coefficient of 1800, outer hot heat transfer coefficient is 1250, and there are fouling also occurring, so that the overall heat transfer coefficient based on the outer surface area will be smaller than these two, 487.1. So this overall heat transfer coefficient value is to be used to calculate the heat exchange in the heat exchanger. So this particular problem is just as a demonstration how to calculate the overall heat transfer coefficient if it's not given in the problem. In certain questions, even HI and H out values will not be given directly. In those cases, from the Reynolds number and the Prandtl number values and the flow configuration, we are required to calculate the HI and H out, and then from HI H out values we need to calculate UI or U out. There are questions being asked for university examination also, which require the calculation of HI, H out, etc., and from that we need to calculate U, and after that we need to calculate the total heat transfer or any other missing parameter like area of the heat exchanger or length of the heat exchanger, etc. Now we can see another question. So I'll read the question. Water at a mean temperature of T mean equal to 80 degrees Celsius and a mean velocity of U mean is equal to 0.15 meter per second flows inside a 2.5 centimeter inner diameter thin-walled copper tube. Atmospheric air at T infinity equal to 20 degrees Celsius and a velocity of U infinity equal to 10 meter per second flows across a tube. Neglecting the tube wall resistance, calculate the overall heat transfer coefficient and the rate of heat loss per 1 meter length of the tube. Here I'll try to, what type of a heat exchanger is that? This cannot be considered as a heat exchanger. This is just a circular tube, and through the circular tube hot water flows. So water at a mean temperature of 80 degrees Celsius flows. So this will have an inner temperature, inlet temperature, and will have an outlet temperature, and mean temperature is the average of inlet and outlet temperature. So 80 degrees Celsius, and there is a mean velocity of 0.15 meter per second through the diameter is also given. Now the heat from the water loses to the surroundings by convection to the air which blows over the surface, across the surface. So this figure shows the view if we see from the top. If we see from the top, we can see that water flows inside the pipe at a velocity and at a temperature having a diameter, etc. And air flows over the pipes, externally over the pipes. So now we are asked to calculate the overall heat transfer coefficient and then the rate of heat loss. So to calculate the overall heat transfer coefficient, we need to know the values of HI and Hout. So here none of these values are given directly in the problem. Rather, the velocity with which it is flowing and temperature, etc. are given. So now we need to calculate the heat transfer coefficient at the inner surface as well as at the outer surface. So how to calculate this? For this, we should use our knowledge for calculating the overall heat transfer coefficient for inner flow as well as external flow should be used. So for that, we will have suitable correlations from the data book and use the suitable correlations from the data book and calculate HI, Hout, and from HI, Hout values we can calculate the overall heat transfer coefficient. So let's see how is it done. Now to calculate the heat transfer coefficient the inner surface, we need to consider the internal flow. Flow inside a pipe is called the internal flow, whereas flow over surfaces, either flat surface or over circular tube or over aerofoil section, etc., are considered as external flow. So we will consider the internal flow and external flow separately. So first we consider the internal flow to calculate the heat transfer coefficient at the inner surface. For that, normally the method of calculating the inner heat transfer coefficient is first we calculate the Nusselt number. And from the Nusselt number we calculate the heat transfer coefficient. So to calculate the Nusselt number, we will have a suitable correlation. Nusselt number as a function of Reynolds number and Prandtl number. In internal flow, first we need to calculate the Reynolds number, and to calculate the Reynolds number, we need to take the property values. Reynolds number is equal to average velocity into characteristic dimension divided by kinematic viscosity. So we should get the value of kinematic viscosity to calculate Reynolds number, and also we need a Prandtl number to calculate Nusselt number, and also we need a conductivity of the water to calculate the heat transfer coefficient from Nusselt number. So kinematic viscosity, at what temperature shall we take the properties? In internal flow, we will take the properties of the fluid at the mean temperature. Mean temperature is normally taken as the average of inlet and outlet temperature, but it is given directly in the problem. So at 80 degrees Celsius, kinematic viscosity, you can get the value of kinematic viscosity from data book, and which is written here as 0.365 10 raised to minus 6 meter square per second. Kinematic viscosity. Conductivity of water is equal to 0.668 watt per meter degree Celsius, and Prandtl number at 80 degrees Celsius is given as 2.22. So knowing these values, now from these values, using kinematic viscosity, we can calculate Reynolds number. Average velocity inside the pipe into characteristic dimension, here is the diameter of the pipe, and kinematic viscosity. Substituting the values with the proper units, we will get the Reynolds number is equal to 10,300. So Reynolds number is a dimensionless number, and knowing the value of Reynolds number, we need to decide whether the flow is laminar or turbulent. So for a circular pipe, below 2300 flow is laminar, and above 2300 we can consider the flow to be turbulent. So this is above 2300, and we need to use suitable equation for turbulent flow inside a pipe. So an equation which can be suitably used, very common equation which can be used suitably is the Dittus-Boelter equation to determine the heat transfer coefficient, the inner surface, which is given by 0.023 into Reynolds number to the power of 0.8 into Prandtl number to the power of 0.3. Care should be taken that the fluid which is flowing inside the pipeline here is getting cooled. This fluid is getting cooled. So if the pipe fluid is getting cooled, then in Dittus-Boelter equation, the exponent of the Prandtl number, this will be 0.3. If it was a heating of the fluid, then this exponent would be 0.4. I just mentioned about that only. The condition whether it's 0.3 or 0.4 etc. are given along with the equation in the data book. So you don't need to worry about to learn this by heart. You can just choose these equations, but whenever we choose an equation, make sure that equation is valid for that particular case, and all the conditions given along with the equation also satisfied. So now substituting the values, will get Nusselt number is equal to 0.023 into Reynolds number to the power of 0.8 into Prandtl number to the power of 0.3. Substituting the values, we will get Nusselt number is equal to 47.4, and Nusselt number is equal to HD by K, or heat transfer is equal to, heat transfer coefficient is equal to Nusselt number into K by D. K is the conductivity of water and D is the diameter of the pipe. So we will get substituting the values, the heat transfer coefficient is given by substituting the values 1267 watt per meter square degree Celsius. So this is the heat transfer coefficient at the inner surface. Now we need to calculate the heat transfer coefficient at the outer surface. To calculate the heat transfer coefficient at the outer surface, we should know what type of a convection is that. Outer surface, the outer surface is cooled by blowing air over the surface, across the surface. So here the characteristic dimension again will be the diameter of the pipe if it is flowing across the tubes. It is an external flow, it is air. So for convection over across a tube, then the suitable equation should be chosen from the data book, and for that also we need to calculate the Reynolds number for air blowing over the surface. So to evaluate the physical properties of air, now for external flow, the properties values are to be calculated at the film temperature, but in internal flow, that is in pipe flow, it is to be calculated at the mean temperature only, but here it is to be calculated at the film temperature. So how to calculate the temperature, film temperature? It is calculated as the average of the surface temperature and the ambient temperature. So what is surface temperature? It is mentioned that the mean temperature of water is 80 degrees Celsius. In the problem, it is mentioned that mean temperature is 80 degrees Celsius. And we are also given the freedom to neglect the tube wall resistance. If we can neglect the tube wall resistance, the surface temperature will be same as outer surface temperature will be same as the inner surface temperature, which is also almost equal to that of the water temperature, average water temperature. So this is taken as the surface temperature. Therefore, so that is one assumption to be made in this problem. Therefore, the physical properties of air is to be calculated the air film temperature, which is the average of 80 plus 20 by 2. We do not know any other temperature, so we are forced to take this approximate value of the film temperature 80 plus 20 by 2 equal to 50 degrees Celsius. So we will calculate the properties of air at 50 degrees Celsius and we'll take the values from the data book suitably. So at 50 degrees Celsius for air at 1 atmospheric pressure, the kinematic viscosity of air 1.822 10 raised to minus 6 meters cube per second, and the conductivity of air, which is very small, 0.0281 watt per meter degree Celsius, and Prandtl number is approximately 0.703 at 50 degrees Celsius. Using this value of kinematic viscosity, we will again calculate the Reynolds number, and Reynolds number is calculated as the free stream velocity into diameter divided by kinematic viscosity. So air is blowing over the surface at 10 meter per second. So 10 into 0.025 divided by 18.22 10 raised to minus 6. Care should be taken to take all the values in SI. So that Reynolds number equal to 13,721, and 13,721 we can, this is actually for this value a suitable equation to calculate the Nusselt number is chosen from the data book. You can refer to the data book and use this equation. Remember, such a physical case has not been solved by us, but it's quite possible that this can be asked for the examination. So Nusselt number is equal to 0.4 Re to the power of 0.5 plus 0.06 Re to the power of 2 by 3 into Prandtl number to the power of 0.4. Substituting the values, finally we will get the Nusselt number for external flow is equal to 70.52, and outer heat transfer coefficient is equal to Nusselt number into conductivity of air divided by diameter. 70.52 into conductivity of air is 0.0281 divided by diameter is equal to 0.025. Substituting that, the heat transfer coefficient associated with the air is equal to 73.3. So heat transfer coefficient associated with the water is high and for air is small value. Now the overall heat transfer coefficient after neglecting the wall resistance will be given by 1 U is equal to 1 by HI plus 1 by H out. Even the thickness also neglected. So substituting the values, we can see that 74.63 watt per meter square degree Celsius. Again, kindly notice that the overall heat transfer coefficient will be smaller than the individual heat transfer coefficients. This is a smaller among HI and H out. So the overall heat transfer coefficient will be smaller than this value. So once we get the overall heat transfer coefficient, then the heat loss per meter length is calculated as Q is equal to overall heat transfer coefficient into surface area into delta T, and surface area is equal to pi d into 1, where we need to calculate the heat loss per meter length. So once we calculate overall heat transfer coefficient A into U into delta T, pi d into 1 into overall heat transfer coefficient into T in minus T out. Actually it is water temperature minus air temperature. Substituting the values, we will see that the heat loss to the surrounding is equal to 351.7 watt per meter length of the tube. Again, this is in strict sense, this is not a heat exchanger problem, but still this will help us to use this equation. Now we will solve one heat exchanger problem in the next video. I'll stop for the time being for this video, and the problem 3 will be discussed in the next video.